Okay, so we've got 3/4 of the way there. We're just looking at this last one then, the time period, and we need to work out what the time period equation is going to be. We know the circular motion equation is going to help us out a little bit here. We know that the velocity of an object is given as 2 pi r over capital T. That's the velocity of an object in circular motion, so that's going to be equal to v. We also know from earlier that v is got to be equal to root gm over r, as we showed in the last video. So we can put these two things together and we can have this equation where 2 pi r over capital T is equal to root gm over r. And hopefully if we can rearrange this, we should be able to come up with an equation that gives us what capital T is going to be. The first thing that we want to do is flip it, because at the moment this is at the bottom. We want it in the numerator, not the denominator, so we're going to go with T over 2 pi r. We can flip the other side in exactly the same way. That's going to give us r over capital GM, all square rooted. So now all we need to do is multiply through by 2 pi r, and we've got our equation for t straight away. We're going to find that this is equal to 2 pi r square root of r over gm. There we go. So that there is going to be our equation. We can notice, incidentally, that we've got an r here and an r here. If I wanted to, I could get rid of this r by recognising that r is just r squared, all square rooted. So just by multiplying this by r squared, I can get r cubed up here if I get rid of that. So t is 2 pi square root of r cubed over gm, and some of you might recognise that as a slight variation of the equation that links r and t, which we looked at when we looked at Kepler and the ratio of r cubed to t squared. But that's our equation anyway for t, and all we need to do to work out whether our statement is correct on the time period is to find out what the time periods of t and q are going to be. So that means that we can write Tp, time period for p, is going to be equal to 2 pi square root rp, all cubed, over gm. Okay. Check that's actually shot. There we go. So Tp is 2 pi blah 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 blah. We're now going to work out what Tq is. This time I'm actually remembering to use the capital letter Tq. So that's going to be 2 pi. That's going to be the radius cubed. The radius, of course, is 3rp cubed over gm. So that's going to be equal, of course, to 2 pi times the square root of, well, 3 cubed is 27, isn't it? Rp over gm. So what we're saying is that this is basically root 27 times 2 pi root Rp over gm. And this whole thing, of course, is the time period of p. So the time period of p times the square root of 27 gives us the time root of q, which obviously is nowhere near this, because this one says the time period of p is greater than that of q. And that was a long way round mathematically of showing something that actually should be fairly obvious. If you've got our objects here, if we're looking at them from above, this is the planet that they're going around, or the Earth in this case, and here's the orbit of q, here's the orbit of p. This one here says that the time period of p is greater than that of q. It's saying that it will take longer for this one to go round than it will for this one to go round. We know that this has got a far shorter path, and we also know that it's moving faster as well from the previous question. So obviously p has to have a shorter time period to go all the way around, a shorter time period than q. So that one cannot be correct, and the only thing that is left that must be right is 14a, as we showed you before. Question 15, to round this off, is looking at the force between 2 point charges, and again we're looking at a ratio question here. So we're going to use the same technique as we've used in several of these questions. We're going to come up with an equation for each of these, and we're going to work out the ratio between them. So we know, this is question 15, we've been doing that before. We know that the force between 2 point charges is given as F equals K, Q1, Q2, over r squared. Now this k, of course, is 1 over 4 pi epsilon naught, but seeing as that's not going to be changing, we can just leave it as k anyway, it doesn't really matter. Now the question is, what's going to happen when we separate, or increase the separation from r to 3r? What is going to happen to this force? Now you might be able to work this out straight away intuitively if you know that this is an inverse square law. If I'm going to end up tripling this, and this is going to be 3r all squared, which is 9r squared, it's going to end up as a ninth of what it was before, but we can show that mathematically. So the new force, just to be rigorous, because of course they may not say we're increasing it to 3r, they might say that we're going to increase it to 27.5r, and that might be a little bit more difficult to do this intuitively. The charges are of course exactly the same, so it's Q1, Q2. The only thing that changes is that now we've got this distance of 3r all squared, which we can write as k Q1 Q2 over 9r squared, which is exactly the same as a ninth times k Q1 Q2 over r squared. This thing here is the old force, so the new force is a ninth of the old force. So that means that the answer to question 15 is going to be D, is going to be a ninth of the initial force.